Welcome to Chapter 10, Part 2, which is called Counting. Sounds like a simple title, but you'll find there are some distinct ways we're going to learn how to do this. First problem, everybody misses restaurants, so here's one about Chili's. They've got a 3 for $10 meal, and I've got the menu printed out right here. They want you to choose a drink, choose a starter, and choose an entree. So if we want to know how many total types of meals there are, one way to do this is by drawing a tree diagram. To draw a tree diagram, you need to make space for all of your options. So first I counted from 1 to 29 to show you the space for all of my drink options. Let's say I choose a drink number 4. Let's say that's my favorite drink. After I make that choice to choose drink number 4, I move on to how many options I have for the starter. For the starter, I can either pick a salad or chips and salsa. So that's option 1 and option 2. And then let's say I do pick the salad because I'm feeling healthy. Then I need to choose an entree, and there are 7 entree options, right? So I'm putting 7 more choices. So that's one of my possible choices, is I could choose drink 4, appetizer 1, and say entree 2. Maybe that's baby back ribs. So we have to do this for as many choices as there are. We have to draw, say we pick drink number 14, we have to draw 2 options for a starter, and then on each starter you have to draw 7 options for an entree. Well, I'm not going to do that 29 times. It's just overkill. I'm not really going to finish this step of drawing the tree diagram, but I am going to answer the question of how many entrees are possible. Turns out there's a principle that allows you to do this quickly. You do the number of choices for your first event. So the first event is choosing a drink, 29 choices, times, and this is the key, the fundamental counting principle uses multiplication to quicken how many choices, or to count how many choices you have in the end. So there's 2 options for the number of starters, so we're basically doubling our number of options from 29 drink options to 58 drink and starter options. And then, yeah, you guessed it, we're going to multiply by the number of entree options there are in order to come up with our final answer of 406 possible meals available for $10 via this deal at Chili's. Okay, I just mentioned it a second ago, but we've got this thing called the fundamental counting principle. It's a long mathy explanation, but basically it's just repeating what we already learned, that if you have a bunch of different events, and events are like different categories of choices basically, you multiply the number of options you have in your first event, number of options you have in your first choice, times the number of options in your second choice, and so on until you're done. And then once you've multiplied them all together, that product represents the total number of ways you can do said combined action. So let's use a license plate to try to demonstrate this principle in a different way. This is fake information, I'm pretty sure. I don't think Washington, D.C. actually has a plate like this, but in every state there are some differences in the requirements of a license plate. So it has 2 different letters followed by 4 digits, and then it explains a little bit more about the digits. What I always start with when I'm doing counting problems like this is I start with making blanks. So 2 letters, blank, blank, 4 digits, blank, 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 blank. And then I'm going to write my number of options in each different blank. So my first number of options, it says 2 different letters. Well, assuming we're speaking about the English alphabet, we got 26 letters in the alphabet. It says different letters. So I should not write 26 again here. Let's say my first letter is a C for Clifton. Then how many letters remain for my second option? Turns out it's going to be 25. What if I pick Z for my first one? Yeah, still 25 remain for my second one. Okay, so if it specifies it's got to be different, then you're going to go down in your options. Okay, then it says 4 digits, the first of which cannot be 0. Okay, so this first one could be 1 through 9, but not 0, so 9 choices. And then after it, it says digits can be repeated, and then it says the rest of them don't really care about not being 0, so it's really 0 or 1 through 9, so that's actually 10 options to go here. And since we don't care about repeating, we can just say, yeah, you got 10 options for the last 3. You want to guess what principle you use here? Yep, you're correct. And so I'll bring up my calculator, and the total number of options we've got is 5,850,000. That's a lot of options, but we need a lot of license plates so that an entire state can have distinct license plates. Let's try it again with spelling. How many 5-letter words, and I have words in quotes, meaning they are like arrangements of letters, but they don't necessarily have to spell something that's already in existence, can be made using the English alphabet? So 5-letter words, 1, 2, 3, 4, 5 choices I'm making. English alphabet has 26 letters. So for my first choice, for that first event, I have 26 options. Then if, does it say I can repeat? I mean, let's say I choose F for my first letter. In theory, I can make another F here, so it can still be 26, right? It doesn't say it can't repeat. So that means that the answer to this one is simply 26 times 26 times 26 times, you get the picture. So it ends up being this many choices. But if I change the problem just a little bit and I say no letter can be used more than once, then when I make my 5 blanks, it's going to be 26 options. But then once I choose, say, the letter F, I can no longer choose that. So then I only have 25 options. Let's say I choose the letter E after that. Then I've used F and E and I have 24 options. And regardless of which choice you make, you're going to descend before you use the fundamental counting principle with this. You're going to find that this is a pattern, this descending thing. Great. So difference between allowed to repeat and not allowed to repeat. Just FYI, we're going to see a lot more of this second type than we will of the first type, but I just wanted to show you the difference. This printout didn't turn out right, but this is supposed to be the 7 Harry Potter books. Imagine I've got them and I want to arrange them on a shelf. Obviously, there's one way to do it that's probably the most obvious. Go 1 through 7 this direction, that's one option. But what if I wanted to change it? What if I wanted to go 7, 6, 5, 4, all the way to 1 the other way? That's another option. So far I can think of 2 options. How many options do you think there are total? Well, using the fundamental counting principle, I can do 7 choices. Once I've chosen a book, I can't also put that book in the second position. So 6 choices, 5 choices, and so on. And then when you get down to the last one, it's almost like there's no choice at all. There's only 1 book remaining. So this number multiplied together using the fundamental counting principle is the same as if I fill this in with a one choice, because 1 choice doesn't add to your choices. So this ends up being 5,040. There is a mathematical symbol for when you see this happen, when you multiply all these descending numbers all the way until you get to 1. So keep that in mind that we're doing that manually right now, but we could do it a faster way. It turns out what we're doing is called permutations, and permutations is just another word for arrangements where the order matters. So ordered arrangements of letters or of books or of anything you want. And it says the number of permutations of n distinct objects is n factorial. So this right here is not a really excited definition. No, the exclamation point in math is different than the exclamation point in English. In math, that stands for the word factorial, and you just say factorial. You want to guess what a factorial is? What if I tell you to calculate 7 factorial? Let's see what comes up in our calculator. So you should get your calculator out. You have this button. So I'm going to go 7, and then factorial is under math. It's under PRB, which turns out to stand for probability. So go to the menu math and then PRB, and it's your 4th option. 7 factorial is 5,040. Just the number we saw before when we did 7 times 6 times 5 times 4, all the way down to 1. So you have a new math symbol that you can now use, and I showed you where it is in the calculator. If you want to simplify this, you could of course just plug in 12 factorial divided by 10 factorial in your calculator, but I want to show you a cool simplifying pattern that will be useful on your homework. So 12 factorial is really all these things multiplied out. Oh gosh, my arm's getting tired. Just going to leave it there. You get what I'm saying, right? It goes down to 1. 10 factorial, same idea. 10 times 9 times 8 times 7, all the way down to 1. Do you see a way to make this faster? Since everything's multiplication across the top and across the bottom, you can use some shortcuts. 10 divided by 10, 8 divided by 8, all this stuff cancels out, except for there's still a 12 and an 11 on top, and there's nothing that remains on the bottom. So now all I have to put in my calculator is 12 times 11, which turns out to be 132, and that's the answer to this. You could have multiplied it all, divided by, multiplied it all, but instead, if you are thoughtful about what these factorials, 12 factorial over 10 factorial, really means, you can find some easier ways. Let's try the next one. So you could do 6 factorial times 56, but one cool thing I noticed is that 56 is made up of 7 times 8. So if I'm saying I want to do 6 factorial times 7 times 8, what factorial is that the same as? Turns out it's the same as 8 factorial, because 8 factorial would have to mean 8 times 7 times 6 times 5 times 4, and that 6 factorial can kind of play into that. 8 factorial turns out to be 40,320. So just some cool ways to look at factorials that might help you with your homework. Okay, back to these letter types of problems. How many 3-letter words can be made without repeating? So that's 26, 25, 24. Okay, doing that in the calculator. So we're seeing this descending thing happen again. Okay, how about we do the books again? We do the Harry Potter books, but this time I'm only choosing 4 to arrange on a shelf. I'm going to end up leaving 3 of them out. So I have 7 choices, 6 choices, 5 choices, 4 choices, and then I don't have to choose from the last 3, so they don't play into my answer. You may have noticed that there is a formula to when you stop descending in the factorial. It's almost like this is the beginning of a factorial, but it gets cut off after 3 choices. And this is the beginning of a factorial of 7 factorial, but it gets cut off after 4 choices. So here's the formula that you may already be starting to use in your head. So for example, for the books, you would write this as 7p R, and the P stands for permutations. So again, permutations are arrangements, and we're doing those for the next 2 homework assignments, just arrangements. So the number of permutations of n objects right here, taken R at a time. Oops, how many did we take? We took 4. We took 4 objects, right? So 7 objects taken 4 at a time and then arranged on a shelf has a formula right here. And it turns out to be n factorial, so that's the total number of objects factorial, over n minus r factorial, so n minus r factorial. Okay, so supposedly that's going to give us the same answer as we saw before, that 840. How does that happen? Well, let's expand this and see. Firstly, this is 7 factorial over 3 factorial, clearly, 7 minus 4. So this is 7, 6, 5, 4, 3, 2, 1, all multiplied together. And this is 3, 2, 1, all multiplied together. These guys can clearly go away if I want them to. So what this means is I'm going to end up doing 7 times 6 times 5 times 4. Yep, that's exactly what I did here. So there were 4 blanks. So what I did is I got rid of the last 3 of these numbers to show like a shortened factorial. So you can use this formula anytime you like for permutation problems. All right, thanks for listening to the long video. Good luck with your homework. You can do it.